Intermolecular forces affects properties of molecules. We can see this in liquids in the form of viscosity. Viscosity is how we describe how well a liquid flows. Low viscosity means molecules move very easily over each other, while high viscosity means they move very slow. Think about maple syrup that's been sitting in the refrigerator. Maple syrup, like this, has a very high viscosity, making it very slow in running. If you think about oil, like you put in your car, it's got a thicker viscosity to it, or a higher viscosity to it, meaning that it takes longer for the molecules to run over each other. This is mainly due to the length of the molecules. It's like the difference of rubbing two fingers over each other versus rubbing the palms over each other. Your fingers have a smaller distance to move over compared to your palms. Therefore, the more time a molecule spends in contact with each other, the more internal friction it has, and so it slows down. Surface tension is another property we see in liquids that has a reflectance on intermolecular forces. Surface tension is how much force you need to apply before you actually break the surface of the liquid. Many insects can walk on water because they are able to disperse out their mass on top of a liquid without actually penetrating it because water has such a high surface tension. Vapor pressure is the third intermolecular force-based property, and vapor pressure is the amount of a liquid that will break free into the gas phase before no more can. So if we have a closed canister and we inject a liquid like ethanol into it, what we find is if we wait some time, some of that ethanol will make it up into the gas phase sitting above the liquid. If you've ever taken a water bottle and drunk some of it and then put it in the refrigerator, you find that it often forms droplets of water on top or above the water level on the water bottle. This is also a reflection of water's vapor pressure. Water can escape into the gas phase without actually having to boil because some molecules are moving fast enough they can escape the liquid. We describe the vapor pressure as being a point at which the molecules leaving to go into the gas phase is the same as the number of molecules coming out of the gas phase going into the liquid. Vapor pressure is related to boiling point. That is, when you're at the boiling point of a liquid, you have more than enough energy to get all the molecules to go into the gas phase without it actually ever coming back to the liquid phase. Molecules are moving too fast. Vapor pressure changes with temperature. When we refer to something as having a normal boiling point, and the key word there is normal, then we're saying this is the temperature at which it boils at 760 torr, or 1 atmosphere. We can use vapor pressure to find different boiling temperatures and what pressure they would boil at using something known as the Clausius-Clapeyron equation. The Clausius-Clapeyron equation relates two pressures to the enthalpy of vaporization and the two temperatures at which each situation involves the liquid going to boil.